I hope you can hear me now, right? I would like to thank the local as well as scientific organizers just to follow this thing. I'll discuss a bit about galaxies at redshift greater than 6. Reasons have been discussed in this conference, so I will just go through this. First off, I will present various observational results which are coming from JWST, focusing on my own view why certain observations are important when we are trying to model galaxies. It will be incomplete. You will hear more details on these observations from Yogesh tomorrow. So basic idea of galaxy formation, we know that if you look at the dark matter, basically you assemble a dark matter halo starting from smaller clumps at different redshifts. This is what hierarchical galaxy formation model will do. But what we are interested in is that let it happen in a system which is self-consistent. Then you look at what happens in individual dark matter halos. And typically what happens is that the dark matter is useful for everybody here. For some of us it is useless because you don't see it. Okay? So we are worried about what we can see and what we can analyze easily. So it is related to gas. So when you think of gas, how do you convert this gas into stars and how you evolve them on galaxies? There are various processes involved. One is cooling and collapse. That leads, some fraction of this process leads to star formation. Star formation means you are thinking of a nuclear reactor running for some time and exploding in various forms and transmitting whatever cooked material into the surrounding region. So this can happen in various forms: mass loss due to planetary nebulae stages, stellar winds, or supernova ejections. Okay, so this is kind of one of the things which will happen. But basically what happens is that this can lead to material which is now enriched compared to what was the primordial original material, and this can go through this cycle. This is the cycle which can go inside a galaxy. Of course, galaxy is not an isolated system, it is interacting with its surrounding. So you can also think of mass loss due to large scale winds. That means not only you influence chemically the nearest neighbor to the stars, you will also influence the larger scale structures like IS, IgM in this. So this is the basic picture. The problem is that once you know this, you can model all of them analytically, because you know that if you don't know some number, it is 0.1. If the product has two numbers, 0.1 and 0.1, the product is 0.1. Because this is what you will say that epsilon, eta, gamma, everything is unknown, but the product will be 0.1. So we have played this game some time back, but then I realized that it is not taking us anywhere. Okay, so that's why what we are going to do is that how to address this problem more realistically. Realistically means it's not going to be correct, but as realistic as we can try. So let me just start with this plot, because this is well-known plot for all of you. If you look at the luminosity function which has been discussed yesterday extensively, observed luminosity function, if you compare with the dark matter mass function, you assume that constant mass to light ratio is valid, then this is the well-known curve. It's in, say, nearly 20 years back people have realized. So this curve and this curve are not different, are different. You have to make them same, so people just bend this way and this way. So bend it at different points. Other way of saying is that if constant mass to light ratio doesn't work, you say that mass to light ratio depends on mass. We don't know which mass, because that is going to change, baryonic or whatever mass, right? So this part, high-end mass, we will say what is known as AGN feedback. Other way of saying is that we want to have a system which will heat up the gas in very heavy halos, and it will not allow gas to condense and form stars. So somehow you suppress this cooling and other things. So you need extra heating source, I will put it that way. But people call it as AGN, and I don't think anybody really understand what is AGN feedback. I also don't understand, so I am not going to contest very much here. This part, it is very interesting. You can do it in various ways. Again, you have to suppress the star formation in the low mass halos. So again, two ways of doing is that one is that you displace the gas from the high density region so that they don't satisfy Jeans condition and form stars, or you keep the gas there and keep them ionized so that the pressure is so much they cannot form stars. So there are two feedbacks people talk about. One is called supernova feedback. Second thing is what is known as photoionization feedback. So these are the picture there. You remember this, and I will come back to bending the thing at later stage, and we will use different physics to bend. So this is what I wanted to say. So coming back to JWST, this is well-known plot. Just imagine the redshift range of 7 to 13 or something. You are talking about time scales of 300 to 800 million years. But I was told that when we were doing this thing, there is a characteristic time scale in a galaxy called free fall time. It is of the order of 10 to the 8 years today. It may be 10 to the 7 years at that time. So it already puts the problem. We are talking about tension. I never use tension because I don't work on cosmological parameters. We'll call it as physics problem here. The time scales are going to be problematic here. That's what you have to remember. Okay, having said this thing, let's go through some of the observational things, and I will highlight few issues we should be aware of in addition to luminosity function while modeling a galaxy. So these are the 4 highest redshift galaxies for which spectra are known, and we believe the redshifts are correct. So you can see that this is the spectrum, and we imagine that it should have gone like this because we believe in everything is a power law, right? Because another thing, if you don't know the functional form, it's a power law. Okay? Of course linear, but second order is power law. So if you consider a power law, there is a break here, and people believe that this kind of break happens because you are at the rest frame wavelength of Lyman alpha transition, and these photons cannot come out of these galaxies to us because of whatever happens in the intergalactic medium surrounding these galaxies. So it's amazing. If we do it 10 years back, take one transition and say that I will measure the redshift, people will laugh, correct? But now we are saying that this is the correct redshift because this is what is being predicted in the standard framework of whatever we call cosmological, whatever, Big Bang cosmology, right? So we will go by that. So these are the farthest galaxies for which redshifts are measured. That means galaxies are there when the universe is about 300 to 400 million years old. So this we will say. The second thing is that we are detecting them because they are in a neutral universe. See, otherwise this thing will not be there, then you will not be detecting them because there are no other features which you can detect. By the way, I want to make a technical comment. JWST provides spectra, but they are at utterly low resolution. So detect lines and all are going to be extremely difficult. So we should keep this in mind. So it's also a technical issue. It's not only physics issue. However, JWST is very good if the redshift is around 8, okay, 8 or 9. You can clearly see nice, beautiful lines which you can use to characterize various quantities, like as I mentioned here, it provides optical to UV spectrum. That means you can characterize the amount of light which is present. You can characterize the amount of metals which are enriched because you are detecting oxygen, sulfur, nitrogen and all. You can also characterize the amount of radiation which is present because if you take resonance lines like magnesium 2 and all, the intensity is directly proportional to how much ions are present in the galaxy itself. It's like volume density of total mass of ions will be directly proportional to the recombination. So they will tell you about how much regions are ionized. That means what kind of stars you have which can keep them ionized. But you interestingly also detect forbidden lines and semi-forbidden lines. Forbidden lines and semi-forbidden lines are dominated by collisional excitations because standard excitations are not allowed. That means they probe what is the pressure in the medium. So it's very clear. If you are looking at spectra, you get much more information than looking at SEDs or doing luminosity function because you can now say what kind of stars are there, what kind of enrichment has gone through. See, I am saying 300 million here. If I am going to detect oxygen and nitrogen at a level of 1/10 of solar, it could have gone through at least 2 cycles of star formation. A typical cycle will last about 100 million years. So it's amazing for you to say. So these are the problem I want to highlight rather than saying that whether it is dark matter or not. You fix the dark matter, even then we have problem. That's the thing I wanted to go through. Of course, the way people measure redshift, I told you the same. Look at the spectrum here and the break here. You can now measure the redshift, and people are bold enough to measure stellar masses. They will tell you what is the mass. And people also know that if you measure stellar mass, you can tell what is the dark matter mass. I am very scared, but people are doing it. So this is what is leading you to the situation in crisis in cosmology. So we have to be aware of this. But I guess that you will hear more from on this photometry, what all can be done from Yogesh, I guess. Okay. So let me come to the luminosity function. It has been discussed yesterday. So I will focus on couple of these plots. One of the things which emerged from early observations of JWST is that we have large number of sources compared to what was predicted before. So what was the idea before is that up to redshift 6 you do all astrophysics. If you are actually measuring the evolution of number density of galaxies beyond redshift 6 up to 10, Hubble data suggested that you don't need anything else, you just look at the evolution of dark matter. It was absolutely, this number density evolution was just like number density evolution of dark matter. So people said that physics somehow freezes beyond this. So that has somehow it has to change. So I will just start like this. Luminosity functions beyond redshift 7. We have issues because this has been discussed, but I wanted to tell in recent observations are bringing the number density closer and closer towards what one thinks is the real life observations. So I will stick to a review kind of thing. So what do you think is the problem? Problem is that you measure photo Z. You don't know what fraction of these photo Z are correct. So that means like the number you are quoting is an upper limit in that sense. Second thing is that you do SCD fitting. SCD fitting has two issues. The break, if the break is occurring at low signal to noise region, you are not sure whether the break is a real break or some highly resonant objects which if you go towards blue end, signal to noise will be bad anyway. If you have ever used spectrum, you will know that if you go towards blue, any telescope, irrespective of, it is related to the instrument configuration. So the end where one is detecting edges, people don't probe them properly. Okay, so this is what we have to remember. Third thing is cosmic variance. The kind of volume people have probed is very small. So this is what is being told here, and look at this blue color plots and look at this. The difference between them is that one is about 4 pointings of JWST, another is 26 pointings of JWST. And there is a plot which shows that as you increase the number of pointings, that means you are increasing the volume probe, you find that the number densities are going down. So for some reason people have picked, I think this is known to you, right? If you are, maybe some of the younger people don't know. When Hubble went, the same crisis happened at redshift of 5 or 6. Lobacheur published very massive galaxies from 10 to the 12, and there was crisis in cosmology to explain redshift 6 galaxies. There are several papers written, but slowly now they are all disappearing. They are all redshift 3 galaxies, wrongly identified when the spectra were taken. So I will not jump into this conclusion and bandwagon. I think that is for people. Yeah. So that is the situation here. Then we need to worry about photometric calibration. It was also found out that the flux what you measure translate to luminosity. Since you are measuring at very large distances, even small error in flux will add to large error in luminosity because of DL square is very large. Okay. And I will just make a comment that don't trust any stellar mass estimation. They are wrong. Okay. So it's clearly. So having said that, I will say one more thing which is interesting is that people are measuring sizes, and the size evolution is something like this. And typically 5 10 to the 10 stellar mass of galaxy has a size of less than kiloparsec. Again, if you do physics like me, because I can't think of higher end physics, you just to see that volume. If I take sphere, radius is 100 or 1/10. That means volume density is 1000 times more. Even if you say that I have the same scale height, this is 100 times more. And people know that it is very difficult to compress a disk gas to that, right? So because you are going to have the same Jeans criteria because mass is same. So it's very interesting for us to realize this. So if you want to do all these things, so last part, okay. Another one more complication I will do, and then probably the next one I wanted to concentrate on is related to these emission lines. These emission lines are now detected by stacking the galaxies. Suppose if you have 200 galaxies for which spectra are taken, you stack them in different regions, you detect them. What does one find? You can actually do one example I will show. You can actually do what happens to carbon to oxygen versus nitrogen to oxygen as a function of abundance here. So this is our local universe. Local universe, this trend is very much understood from the stellar evolution. So if you look at carbon to oxygen, it follows this trend which has been set by the local universe. Whereas if you look at the nitrogen to oxygen, this is the trend set in the local universe. I will explain why it is if somebody is interested. But we find that in the observation at high redshift, nitrogen is enhanced. This suggests that you have to go for a population which is slightly different. So, okay, I think I don't know. The last bit, one more. So I have too many things to say. Maybe I'm worried that I have to go to what I wanted to do. The other thing which is complicated, maybe this is important for everybody to realize also. Other thing which is complicating is what is known as little red dots. Little red dots are the objects which are seen with red dots. If you go and look at the spectrum, they behave like a AGN. Okay? But if you look at the blue part, you see they are like stars. The red part, they are like AGN. It is always ulta of what you see in nearby galaxies. Nearby galaxies look red, quasar look blue, because it is the other way around. So if you look at the number density of these typical masses are of the order of 10 to the 7 solar mass. If you look at the number density per unit volume, it is 1/10 of what you see for galaxies, or 10 times more than what you see for population of AGNs. So if you trust that these are black holes, which is what people tend to believe, So you already have too many black holes to deal with at redshift of 7 or 8. So you will say we will deal with it, there is no problem. The problem is that this population simply disappears at redshift 3. So it seems that there is a new set of population which we need to understand. So to understand all this, okay, we started, I think I have to say this, I will take a couple of minutes or 1 or 2 minutes just to say this. We started this what is called the NICER IUCAA new simulation of JWST galaxies. We already hear about it, so I will not look into the details. This data will be available. The idea is that we can run this simulation in 10 days time up to redshift 4. So if I have 100 days, I can do 10 at least parameter space variations. This is amazing to do, and just to apprise you of what kind of sizes we have, this is the thing you are aware of. This is TNG simulation, and you can see this is the kind of box sizes they use, and this is the kind of box sizes, this is the kind of number of particles. So our numbers are close to something like 2040 cube particles. This is what we are simulating, and the simulation boxes are 50, 100 and 250 megaparsec. Here we can actually do feedback variations, and so I see standard picture to show we can do. This is for Yogesh, and he will name this galaxy at some stage. This is the redshift redshift 6 spiral galaxy in our simulation. And this I will skip because these things you heard from, this is one thing I wanted to do. I just give you the power of such simulations. So this is the same galaxy in the dark matter. In one case, all feedback will go with some speed of wind. In another case, it will go with half the speed of wind. Other way of saying is that wind carries a momentum which is half that of momentum in the other simulation. This is what we can fix, right? We can fix that what kind of efficiency at which wind is propagated. And the same galaxy, it has 42,000 stars when the winds are slower. It has 26,000 stars when the wind goes faster. And you can see it is like a razor thin disk. If you see, is much more bulgy. Actually, if you do calculations, you can see that the sizes of the galaxies are very much depending on the feedback we are putting. So I want to say that in analytical model, you can say that I will suppress this by doing this. If you do this, we run into difficulty of understanding the sizes of this thing. So of course, these things were discussed. I will not go into these plots. The last plot I want to say is that this is the last plot. So we also are now able to do this calculation which I skipped, and this is my last slide in that sense. So since this guy is sitting in each galaxy is sitting in the web of intergalactic medium, you can actually ray trace. You take each star and calculate what is the opacity it will face in the interstellar medium, intergalactic medium, before going to the intergalactic medium, circumgalactic medium and intergalactic medium. What we are finding is very interesting because maximum optical depth comes from the galaxy itself. Suppose you say that I remove the galaxy contribution by some physics, okay. You go up to some distance, then you look at the IGM. It is, what we are noticing is that it's very interesting. The second dominant factor is not the IGM, that's the clustered IGM. In the sense that there is an intermediate scale where is the enhancement of baryonic matter around this. At present it is done in an ad hoc way. I would like to have a simulation done with a proper radiative transport, which is what we are hoping to do. So these are the, what more can be done. So these are the things we can do. Getting black hole number density correctly, we have some issue in getting the black hole number density. It depends on seeding and various things. We are, out of these 10 models, couple of models will explore how to get the correct black hole masses in little red dots and simultaneously explain quasar luminosity function at redshift 6. This is our aim. We can produce millimeter, C2, C1. We heard in the first day all these lines which are seen from ALMA, which can be easily produced because we have all the tools, and this will not have alpha and beta. Okay, that's what. I don't know, people didn't get the joke. Reionization models, we have to do post-processing step. If we do it, we can also run the models with multiple radiation field in this way. Running that's what, patchy reionization. Dust and Lyman alpha radiative transport, I think this is going to be a very serious problem. People are talking about F escape. What F escape? F escape is 0 for continuum photon. You are talking about line photon. So I will be bit worried about Lyman alpha transport as well as Lyman limit transport. Radiative transport outside the galaxy is very interesting also. I think we want to look at metal lines. I think this is what Prakash is trying to do. Couple of simulations have come up to redshift 0. And I will tell you that these simulations are far superior than some of the things you guys are using, like Sherwood or some bit of even Illustrious TNG. So these simulations can be available to people who want to work on it because it's going to be raw simulation. It's not going to be as good as Illustrious simulation in the product wise, but If somebody wants to work on it and get the products, we can study CGM, we can study cross correlation between Lyman alpha and galaxies and all. So I'll stop here.
Thank you. Time for questions. Okay, let me start from here.
Yeah, I mean these little red dots, if they are AGNs, they should show up in X-ray, right? But if I remember correct, that was one
No,
of
they
the
will not
issues.
show up because you see they are red, right? They are red. So if the redness means there is dust and there is high column also. So X-ray will also be absorbed.
So then X-ray background will not be a problem, even if
Hard
you have-
X-ray will be a problem. Soft X-ray is not a problem.
So hard X-ray because they are escaping.
Yeah.
Okay, okay.
So that we are not observing. That is the thing. That is one thing we calculated. That's what we are trying to calculate, hard X-ray and soft X-ray background. Other way you will say is that if it is isotropic dust or in one side, see that is other way of looking at. You put tilted red dots in all galaxies, then take 10%. That can be ruled out. So that we can rule out by saying that X-ray background will be there.
Yeah, yeah.
But if it is isotropic scatterer, then we cannot rule out.
And about these high redshift galaxies, I mean, what you are saying is even now when we call spectroscopic conformation, that is also not very solid because the
Spectroscopic
resolution.
conformation is solid. The individual galaxies are solid. Only thing I have is that, see, it is my ignorance, I am not blaming anybody, is that I don't know how to calculate volume. See, converting one or two detection spectroscopic candidates based on color cut to convert to luminosity function, I have not understood. I will not say, so I cannot make a comment on that.
Hi, thanks for the nice talk. So I have two questions. Because you mentioned about ACD fitting problem and you mentioned about high nitrogen in high redshift, how do you put this together? How much do you trust it?
See, high nitrogen is different ball game because I think don't mix to this thing. Nitrogen issue is I want to understand how to model N3 line. See, N3 line, these guys are modeling through what is known as equilibrium ionization. But if I say the time scale is very small, why should I believe in equilibrium? I think that is what it is. It is not a nucleosynthesis problem. It is a non-equilibrium problem. So we will
Or
address
not
it.
chemical composition of galaxies?
We have to try here. I don't know. I cannot say something which I have not done that. But I believe this is the reason.
Okay. Maybe I'll go later.
Maybe we can discuss in, okay. One question.
You were saying that we start to see emission lines by the redshift of 8 or something, and those two galaxies that are at the redshift of 14, they are identified with just breaks. But a new paper has come out like not too long ago by Naidu et al. And that galaxy is at around the redshift of 14.4 and it has multiple emission lines visible also. So
No, I think other multiple emission line visible is not a problem. Visibility of Lyman alpha emission is a problem. Because all other emission lines can be produced where they are proportional to what is the star formation. Because I mentioned that the density of gas is very high. When the density is very high, the recombination goes as n square. Okay. So if you simply scale ISM densities to that kind of density we are talking about, it's natural to get lot of emission lines. I am not worried. But what everybody is worried is that redshift 14, how come you are having Lyman alpha? Because Lyman alpha should not be seen. Because redshift 14 should be sitting in a very dense intergalactic medium. So that is the issue. If, see, 1 is never a problem. The error is 1 plus or minus 1, right? So we have no problem. If people find 10, we will worry about it. That will be my attitude because otherwise I will get BP tablets.
Okay, one last question. Yeah.
So maybe I don't know this, but what is your concern about stellar masses from JWST? Is it that the SED fitting codes have not been independently calibrated by redshift?
No. SED fitting code, see, stellar mass is not computed based on how many stars are there formed today. We need to know how stars are formed ever since the first stars are formed in the galaxy. This is known as star formation history. So people assume exponential increase, exponential decrease are constant or stochastic. So stellar mass, what you infer, in the late stage what happened is the late stage is dominated by, you are convolving with accretion which happened over a large time scale, there is no problem. When you are at very high redshift, you are still in this kind of fluctuating region where smooth curve I cannot fit through. If I want to say how star formation happened as a function of time, I have not yet reached a stage where I can follow a smooth curve. This is a simple way of explaining, because of which there is a huge degeneracy and people come up with whatever number you want. And there are nice papers recently, if you take them as stochastic process, the masses are dramatically reduced. Even for IMF I am saying, even if your IMF is correct, I'm just saying that star formation history is much more crucial than this.
Okay. Maybe we can discuss more in lunchtime. So let's move on to the next speaker. Okay, and thanks to speaker again. Yeah. So our next speaker is Bihag Deve, and he is going to talk about learning from galactic rotation curves, a neural network approach.
This is fine. Yeah. When 5 minutes, right? Okay. All right. Good morning, everyone. I'm Bihag, and I'll be talking about some of the recent exploratory work that I've done regarding using neural networks to do parameter estimation from galactic rotation curves. So we know that rotation curves are an important set of observations at galactic scales. In particular, they're essentially just orbital velocity of stars and gas around the center of a galaxy as a function of radius. And they can be used to understand and constrain galactic scale effects of various theoretical models. That includes models of dark matter or models of modified gravity. And this inference or this constraining is usually done using the framework of Bayesian inference. So where one uses this Bayes rule to construct a posterior, to define a likelihood, and then of course get marginal and joint distributions for these parameters. Now the question that we wanted to ask was essentially, can we use machine learning techniques like, for example, neural networks to do some sort of parameter estimation, to learn parameters from rotation curves. So I'll just briefly recap what the usual approach is. So for the Bayesian approach, we basically have a bunch of data which are just points and they have errors associated with them, and we have some theory parameters that aims to describe this data, and we set some priors for these parameters, and then we define a likelihood function where then we use Bayes theorem to define a posterior, and then we use some sort of Markov-Chain Monte Carlo techniques to sample this posterior and get some sort of a distribution, right? If we use neural networks, because neural networks are incredibly good at approximating functions, one can ask the question, okay, so if you have a bunch of rotation, circular velocities, can we basically learn a function that goes from the space of these velocities to the parameters of the model that we are trying to describe? So can we learn a function which is a nonlinear function which is f as a function of the velocities v and parameterized by something that I'll get to, right? So this is the thing that we are trying to do. And once we train this neural network to learn this relationship between rotation curves and parameters, one would give it the actual observed rotation curves and get the parameters that we actually want. Okay, so what exactly is a neural network? I'll very briefly go through this. So suppose there exists some potentially complicated relation or complex relationship between the input x and output y, and this input x and y could be vectors, could be y could be categories that we are looking for. So all we need to construct a neural network are just observed samples, basically observed samples of known pairs of inputs and outputs, x and y's, and we can construct a function f, which is a function of all the inputs parameterized by the so-called weights and biases, and the entire point of training a neural network will be to optimize the parameters omega, which are the weights and biases, such that the output of the neural network is close to the expected output. And this closeness we basically define using something called a loss function, which has to be minimized. Right, so lately there has been a lot of interest in using these neural networks to conduct parameter estimation. So there are a couple of ways in which this is done. One way is to basically speed up Bayesian inference. So instead of solving, for instance, Boltzmann codes to get CMB spectra or matter power spectrum, we basically emulate these processes using a neural network that speeds up Bayesian inference at the end, right? One can also use neural networks to mimic various parts of the Bayesian inference pipeline. For instance, to directly basically obtain the posterior or learn the posterior from using various techniques, complicated techniques like neural posterior estimators or neural ratio estimators. However, these two work within the Bayesian inference framework. Another way of approaching this is to do direct parameter estimation, the thing that I had described earlier, where you learn the relationship between data and parameters, and then you give it observed data to get parameters directly. This does not fall into the purview of Bayesian inference in some sense, and this is something that we will be looking at in a very simple scenario with a very simple neural network. And this has been recently explored by for the case of cosmological parameters from H of Z data by Shrikanta Pal and Rajiv Saha, for cosmological parameters of CMB spectra by J.G. Wang, and of course axion string parameters from CMB maps by Hagimoto and Mustafa Amin. So very quickly, galactic rotation curves are essentially, as I had mentioned earlier, circular velocity of gas or stars as a function of radius. And of course, we know that luminous mass in a galaxy is often not enough to describe observed rotation curves, so we need some additional component. So this additional component, in some sense, it could be modified gravity, it could be dark matter. We'll be considering in this talk dark matter. So basically what we'll want is an additional dark matter component which we can parameterize, added to the already existing baryonic component that has been modeled by the Spark database, and we basically try to see how close to observations we can get. Right? The dark matter model, to basically talk about, very briefly introduce dark matter. What do we know about dark matter? We know that it's non-relativistic in that its pressure is much smaller than the rest mass energy density. We know that it consists of, it accounts for 85% of the total non-relativistic energy density of the universe, or 25% of the total energy density of the universe. And we know that it has small or negligible couplings to standard model particles, except gravitationally. And what do we not know is basically everything else. If it is a particle, we don't know the mass of this particle, we don't know whether it's a boson or a fermion, and we don't know whether self-interactions of this dark matter particle are important. The model that we'll be considering in this talk will be scalar field dark matter, where we consider a spin 0 boson with mass much smaller than order 10 eV, and given observations of the local neighborhood of the dark matter density in the local neighborhood, as well as a typical velocity of dark matter particle in a galactic halo, we know that if mass is much smaller than order 10 eV, the de Broglie wavelength will be much greater than the interparticle separation, in which case we can describe the collection of these particles using a classical scalar field. And this is exactly what is done in the paradigm of fuzzy dark matter, where the equations of motion in the non-relativistic weak field limit are essentially just the Schrödinger-Poisson system, where psi mod square has the interpretation of mass density. So these equations also admit steady state solutions called solitons, and if mass is of the order of 10 to the power minus 22 eV, and the corresponding de Broglie wavelength will be order kiloparsec, so we can form these solitons at the centers of galactic halos. And one have, over the last 10 years, there are very interesting effects at galactic scales because of this large de Broglie wavelength that have been explored to constrain these dark matter models. And essentially what has happened is the most interesting mass range, mass of the order of 10 to the power minus 22 eV, has been effectively ruled out by various astrophysical observations. Here I have not mentioned the constraints mentioned yesterday by Professor Raghunath and Professor Shantanu as well, but that also basically constrain M of the order of 10 to the power minus 22 eV to not form all of dark matter. So the question is FDM ruled out? Well, I won't be answering the question in this talk. It will be, because all of these constraints have not considered the effect of self-interactions, which will be discussed by Gaurav Goswami tomorrow. So today we are just going to deal with this very vanilla kind of FDM model and see what neural networks can do here. Right? The parameters of interest are as follows. Because the dark matter density profile in the case of fuzzy dark matter has a flat density core at the inner regions and NFW-like halo at the outer regions, we characterize this by just a rho dm as shown in the as shown over here. So we have a flat density core in the inner region and an NFW-like envelope at the outer region, and this entire density profile is parameterized by these four parameters, which are mass of the FDM particle, a scale factor which is related to the mass of the soliton, transition radius, the radius at which the core transitions to an NFW envelope, and RS, which is just the NFW scale radius. We can tune the baryonic contribution by the stellar mass to light ratio, and we are considering dwarf bulgeless galaxies because the contribution of dark matter is greater at all radii for such galaxies. Right? The modeling for V disk and VG is already given by the Spark catalog, so we won't be touching that. We'll just be tuning how much they contribute, in particular this disk component. Right? So the parameters that we have are 5 parameters: epsilon d, ms, rt, and rs. Right? The neural network that we are looking for essentially has rotation curves as input and theory parameters as output. So what do? Well, we take some uniform distribution of these parameters initially, and we draw many samples from them. We we obtain basically the density profile and then the theoretical rotation curve. We consider these to be our simulated rotation curves, and we use these to train an untrained neural network where the ground truth are the values of the parameters that we started with initially, right? Once this is trained, we actually feed it the observed data, observed rotation curves, and then get parameters as predictions, and hopefully uncertainties associated with these parameters is something that I'll discuss. Right? This is the process of generating simulated rotation curve, and in the interest of time, I'm going to skip this. And these are the galaxies that we have considered, the 7 dwarf galaxies, and these are the uniform priors that we give to basically generate our training data. Okay, so the neural network, the architecture of the neural network that we use has been obtained using a grid search for a couple of galaxies because that is quite computationally expensive to do. And we basically use 2 hidden layers and 200 neurons per layer, and we train the neural network for 250 epochs, which is a batch size of 32. And we also include this dropout parameter, and I'll not go into the details of this. But the important thing to know is the loss function. We'll be using initially a very simple mean squared error loss function, which is just the Euclidean distance between the output of the neural network and the expected or the ground truth values. The neural networks that we have will have around 40 to 50,000 weights and biases, and we'll be using around 500,000 rotation curves as our training data, which are split into which are split as 80, 10, 10 into train, test, and validation sets. Right? So once we train this neural network for 250 epochs, you see that the loss has basically settled down after 250 epochs, and we then choose a couple of rotation curves in random from the test set, a set that neural network has not seen during training, and we construct from the parameter predictions, we construct rotation curves to see how well they match, and we see that they match more or less okay, except for this particular one. So the test set is around 50,000 rotation curves. I've only shown 4 randomly drawn ones. And the problem occurs when we actually give it observed rotation curves. You can see that this is quite terrible. None of the fits are really good. So the reason for this is the theoretical rotation curve, if you see for this particular galaxy, if you just remove the baryonic components and we keep the rest and we compare it with the theoretical rotation curve, you can see that the theoretical rotation curve is quite smooth, while the observed DM contribution is quite wiggly. And this is why when we train it on this smooth curve, when we give it something that is a bit bumpy, it does not really recognize how to basically get the parameters. And you can see that where the dark matter contribution is nice and smooth and it matches the theoretical rotation curve, the predicted parameters actually give an okay fit. So what do we do to fix this? We add noise to the training data. So already rotation curves come with observed noise. So for every simulated rotation curve at a particular radius, we add an additional term which is just a random draw from a normal distribution with 0 mean and the observed uncertainty as the standard deviation. And then we again train our neural networks for 250 epochs, and when we again give it the test set, just the same 4 randomly drawn rotation curves, and we see that it's still performing quite well. However, when we give it observed rotation curves, you can see that things have drastically improved. The red curves are basically the predictions given by neural networks trained on noisy data, and you can see that for almost all galaxies, this is now fitting quite well with a quite low reduced chi-square, except for this particular galaxy, UGC A444. And we'll get to that as well. However, when we do Bayesian inference, we also expect uncertainties associated with these parameters. So how do we get that? So in this particular way of doing things, we have recognized that obviously observed rotation curves for a galaxy at every radius has some uncertainty associated with it, right? So what we do is to simulate multiple observations. We basically draw at every radius from a normal distribution or a Gaussian distribution with mean as the observed velocity and sigma observed as the standard deviation. So essentially taking 1000 draws from this basically means that we have 1000 realizations of the observation. So, and then we make predictions for each of these realizations. So one can think of this as sampling from the vicinity of the observed rotation curves while being consistent with observations, right? And we basically get a chain of parameters. So this is not exactly an MCMC chain, but we basically get a chain of parameters that we can then use to plot 1D and 2D distributions. And when we do this, well, for some parameters it works remarkably well. For scale, RT and M, it does quite well. However, some of these parameters, the rotation curves are not very sensitive to. For instance, RS and epsilon star. So okay, by the way, here the blue curve, the blue shaded region are the posteriors for the MCMC approach, and the green shaded regions are the not posteriors but 1D and 2D distributions for the ANN approach. And you can see that for these two parameters, where they are not very sensitive, the rotation curve is not very sensitive to them, this approach completely fails. So we need something else. And this is just, I'll just skip this for now. So how do we learn uncertainties better? Well, what we ended up doing was using a different loss function, which is called a heteroscedastic loss function, or sometimes also negative log likelihood in machine learning literature, where we basically introduce this additional parameter sigma ij, which the neural network can predict, but it has no ground truth value, right? So, if the neural network predicts a very large sigma ij for any particular parameter for any particular training data point, this term will blow up, making the basically making the loss very large. So it will have to reduce it. But if it reduces it too much, then this term will blow up, and again, so it will have to increase it. So looking at the training data, the neural network will automatically learn during training itself the uncertainty associated with every prediction that it makes of the parameters. So when we do this, you see that using the MSE loss function and the multiple realizations method, the median values of the multiple realizations method, and the comparing those to the predictions obtained by the heteroscedastic loss function, you can see that in fact heteroscedastic loss function works even better. The chi-square values for almost all of these cases are smaller. And when we compare our uncertainties to the uncertainties obtained from the MCMC approach, you can see that the purple curves, the purple whisker plots are essentially neural networks trained on mean squared error plus multiple realizations. The orange plots are neural networks trained on heteroscedastic loss, and the green plots are the parameter values and the uncertainties obtained from MCMC approach. And you can see that for these two parameters, which were hard to learn for the MSE plus multiple realizations approach, this actually, the heteroscedastic loss function actually works quite well and predicts larger uncertainties as expected from the MCMC approach. So what we have essentially learned is that neural networks require noisy training data when we are dealing with rotation curves. And of course the MSE plus MR model does not really work well, while the heteroscedastic loss model works quite well, but it does not really predict any posteriors. That's one of the drawbacks that we are working on. And the other thing is, we don't really know exactly what the heteroscedastic loss function is learning, because this is not exactly a Bayesian approach. It's not clear what these uncertainties exactly are, but they see the values that we obtain are still similar to the values that we obtain from a typical MCMC approach. And of course, a neural network architecture has not been optimized completely. We think that if we optimize it further, we can improve the speed. And physics-wise, it is important to note that no single value of small m satisfies the rotation curve for all galaxies, which is what we would require if we have a fuzzy dark matter model. We are working on developing a joint analysis method where we train multiple neural networks together to get a single value of m at the end. That's something that we are working on. And also the values of m obtained, which are of the order of 10 to the power minus 23, are in tension with many other bounds obtained from, let's say, stellar heating or Lyman alpha data or Soliton-Hill relation or 21 centimeter observations, basically everything. Of course, the inclusion of self-interactions or multi-field UL can drastically affect these constraints, and that is something that I'm leaving for future work. Yeah. Thank you.
Thank you for finishing in time. Time for questions.
So the sigma square observed is going to be different for different galaxies, right?
Yes.
So how is that included in the training set?
Yes, so that's something I did not mention. We train a different neural network for each galaxy.
And how time consuming is that?
That's,
Compared to
so
MCMC?
on my laptop it takes around 40 minutes to train a neural network.
And MCMC?
MCMC takes around 30 minutes for the entire thing. So here I'm not even counting the generation of training data, which takes time. That's why the optimization of the neural network architecture will improve the speed further.
Okay, thank you.
Can you go back to the previous? Yeah.
This one?
Yeah, this one. So You see you get a two-sided error bar, which means your data prefers, an ULDM mass. It's not an upper bound or lower bound. And you see it where, as you pointed out, you see each galaxy preferring a different value. Isn't that a sign of some missing systematic in your model?
I see what you mean, right?
It's not just here, there are SIDM papers with similar plots.
I see.
And that seems to me to be a sign of a missing systematic.
Okay, that is something that we have not considered, but I'll think about this.
Yes. Ranjan.
Hi, Vivek. Thanks for the very nice talk. So I may have asked you this question, but I've forgotten the answer. That's my fault. So if you do multi-field ultralight dark matter, do we know? How the multi-fields will be distributed inside the galaxy? Is there any theoretical estimate studies about
So there have been some recent simulations by Box and others.
Yes.
They basically, the density profile will be, so the inner region will be dominated by the heavier mass, and the outer region will be dominated by the lighter mass.
So then it's just NFW, right? Because the lighter mass will do the soliton at the center, right? If you put
No, so it will be a two soliton kind of a thing, where it will have a flat thing, it will go down and again have a flat thing and it will go down.
Okay, thanks.
Yeah.
Thank you very much.
Rajiv.
So in the Bayesian framework, you typically want to ensure that your posterior is not prior dominated, right? You are not computing any posterior here.
Yeah.
How do you ensure that in this framework?
So that we do not really do that.
So then, how would you actually go about and trusting these constraints?
So so what we have essentially done is compared it with the standard MCMC approach, right? So the benchmark that we have set is, okay, if MCMC with the same prior is giving you this, can neural network reproduce that?
Hi, Bigha.
Yes.
Thank you for the nice talk. Just a follow up on the first question you said, for in your training data set you have multiple rotation curves. For each rotation curve you said you'll train different neural networks, is it?
No, not for each rotation curve. So for each galaxy we have a different neural network.
Sure.
And we have around 500,000 rotation curves for that particular galaxy. So simulated rotation curves.
But finally, when you have some test data, when you have some real data or some unknown thing, you have to pass it through a single network.
Yes, we pass it through a single network.
Okay, thank you.
So just a clarification again related to the earlier question. So maybe I missed this. So can you tell me what is the parametric dark matter profile you're using? I mean, people have used different in literature.
It looks something.
No,
something
the
like
dark matter. Okay, so
yeah, this is the dark matter density profile.
Okay, so people have used a fourth model which scales as the inverse fourth power at low distances. So have you used that and at NFW at larger distances?
Yeah, so we have used this in the inner region.
Okay.
Yeah. The shift profile.
Okay, fine. Okay, thank you.
Okay, let us thank Bihag once again.
Thank you.
Our next speaker is Deep Ghosh. He's going to talk about bosonic dark matter dynamics. Deep, you have 15 minutes. After 12 minutes, I will signal you.
Am I audible in the back? Okay. So I first thanks the organizer for giving me this opportunity, and I will present this work which is done in collaboration with Professor Kaushik Datta and Professor Bishwarup Mukhopadhyay. So let me begin. So as we all know, the microphysics of dark matter is unknown, and for that we have several experimental efforts. In particular, in direct detection experiments, we probe this dark matter nucleon cross section, and whereas in indirect detection experiment, we probe the dark matter annihilation cross section, which is this sigma v. But till now, we don't find any positive signature, and in that regard, mainly to probe this dark matter nucleon cross section, neutron stars can be useful, because in neutron star there are lot of baryons, in particular for abundant baryons in any other terrestrial facilities. So if there is certain interaction between dark matter and neutron, then this neutron star can capture the dark matter and we can probe the dark matter nucleon cross section. So in this work, what I will show, that this is a quick summary, that we can constrain this sigma chi n for both non-annihilating and annihilating dark matter scenarios. And for non-annihilating dark matter, the existence of old neutron stars is enough to constrain this sigma chi n. And if there is some annihilation, then we can use this neutron star surface temperature information to constrain this sigma chi n. And as we know, the neutron star itself is a very complex object because we do not know its inner structures. So for this talk at least, we will assume neutron star as a solar mass compact object and whose radius is roughly 10 kilometers. So now in neutron star residing in dark matter rich regions, it can capture dark matter, and for that we need some non-gravitational interaction. So that is related to this interaction. This is because for this gravitational potential of the neutron star, dark matter comes inside the neutron star, but its velocity is approximately this escape velocity of the star. So it comes and goes out. So we need some interaction between neutron star which can dissipate the energy, and so that it can get captured. And this is a simplistic formula for dark matter capture rate, where this sigma chi n comes, and this is the geometric cross section. And now you can see there is a Xi factor sitting. So this denotes basically the neutron star. In neutron star, neutrons are degenerate. So depending on the dark matter momentum, for the dark matter nucleon scattering, all neutrons may not be available if the dark matter momentum is low enough. So the maximum value of Xi is 1. Okay. So this is the geometric cross section. And now as we can see from this formula, that within a year 10 to the power 33 number of dark matter particles can get captured inside the neutron star. So now if this number of dark matter particles are dispersed over the entire volume of the neutron star, that is over this radius, then its density is roughly this. And if I assume the dark matter particle mass is 1 GeV, then if we calculate the free fall time, then it's roughly 2 years. Now this free fall thing doesn't happen because of this dark matter neutron interaction inside the neutron star, which can brings thermalization of dark matter particles to the neutron star core temperature. And as we can see, the thermalization time is pretty much smaller than this free fall time, which eventually prevent the collapse within the few years. So as you can see, there are a lot of neutrons, so this thermalization time is pretty small than this free fall time. So once the dark matter particles is thermalized inside the neutron star, it forms a dark core, and its radius is given by the temperature of the neutron star and the density of the neutrons, which is roughly this. Now after the thermalization, what happens, these dispersed dark matter particles are confined within a smaller radius. So that means inside the neutron star, density of the dark matter increases, and hence the free fall time also decreases to 6 seconds. But there is thermalization, so that means there is some pressure, and related to the pressure there is another time scale which comes, which sometimes called this sound crossing time, which is rather small than this one. So this dark core collapses only when this free fall time is smaller than this sound crossing time, which implies that this density, this dark matter density inside the neutron star should be greater than the neutron density. So now the real question is, can we achieve this kind of condition for an old neutron star? So now as you can see from here, that this radius depends on the neutron star temperature, and neutron star temperature is decreasing over the years. It starts from, let's say, from 1 MeV and it goes to around EV. So, so we can achieve this kind of condition because dark matter is confined to, let's say, around a centimeter scale. So then we can achieve this condition. So then this dark matter core can collapse, and it collapses to first a tiny black hole inside the neutron star, and then this tiny black hole can devour the entire neutron star and transforming it into a solar mass black hole. So now this formation of this tiny black hole and its evolution to a large black hole depend on the thermal state of dark matter particles, because there is an interplay between this gravitational force and the pressure due to thermalization. So, so this depends on the thermal state of dark matter particles, and it is even become very important if dark matter is bosonic, because for bosonic dark matter particles, these bosons can form Bose-Einstein condensate inside the neutron star. And for that we have to satisfy this condition that neutron star temperature should be less than this critical temperature, and this critical temperature depends on dark matter ambient number and this thermal radius. And if the dark matter is in a BEC state, then for the dark core to collapse we need this amount of dark matter number inside the neutron star. And if this is in the non-BEC state, then you can see we need more particles. This is simply because in the BEC state, this is a kind of a pressureless state, and for non-BEC state there is some non-zero pressure. So for that reason we need greater number of dark matter particles. So from this expression, as you can see, that this collapse business depends on ambient neutron star temperature and the dark matter abundance inside the neutron star. And in most of the previous studies, this analysis is performed with a constant neutron star temperature, and while this thermal state of dark matter is taken as an input. So in this work, we dynamically determine the thermal state of dark matter and subsequent black hole formation, taking the neutron star temperature evolution into account for given dark matter values, dark matter parameter space of this sigma chi n, sigma v and m chi. So let me show you the first result. So, so here you can see this is a typical case where dark matter is non-annihilating. So this region surrounded by this blue line where BEC forms, and there are two regions which we can exclude from the observation of old neutron star. So this means these neutron stars do acquire dark matter particles, but these are not transmuted to black holes. So from the existence of this neutron star, we can put a bound on this sigma chi n. It means, so there are two different regions. So if you look at here, so if the sigma chi n is above this line, then capture is so high that we would not see a 10 to the power 10 years of age neutron star, but we have seen it, let's say. So then we can exclude this region. So there are two regions coming from this condition, because for BEC state the collapse condition is different, and for this non-BEC state the collapse condition is different. So there are two regions of exclusion depending on the thermal state of dark matter. And now interestingly, you can see there is a region where BEC forms but black hole doesn't form. Okay. So this comes from the fact that these black holes form inside the neutron star, these tiny black holes, but it evaporates due to its small mass. So that's why this region is kind of unconstrained. And interestingly, you see that in this region direct detection experiments are still important to constrain the dark matter parameter space, whereas for in the high mass end and in the low mass end, these neutron star observations can be important to constrain this sigma chi n. So now if we put some small annihilation cross section to this scenario, this is annihilating dark matter scenario, then of course these bounds gets weakened. But if the dark matter annihilation products are confined inside the neutron star, then it can increase its surface temperature. So as you can see, please concentrate on this blue line. So without dark matter annihilation, the neutron star temperature goes like this. This is, and if there is dark matter annihilation, so then this curve flattens out, and we can measure the surface temperature from JWST telescope, and from there we can constrain again from in this plane. And another thing, let's so there is a complementarity between direct detection and indirect detection using this neutron star business. So if let's say someday we know the sigma chi and this from direct detection, then it actually fixes the capture rate given the dark matter mass. Then we can put a lower bound on this dark matter annihilation rate. So in this figure, this upper region is excluded from the indirect detection, and in the indirect detection it gives, in this plane it gives a ceiling as from the neutron star observation. It means that if sigma v is above below this line, then we would not see a old neutron star. So we have seen it, so that's why it puts a lower bound on the this dark matter annihilation rate. And again there is a two regions coming from this thermal state of dark matter. So let me end with the fact that up till now whatever I have discussed is based on the non-observation of this kind of solar mass black holes. These constraints are coming from dark matter, from the existence of the old neutron star. But the LVK collaboration is actively searching for such solar mass compact objects, and these objects can be very exciting because there is no known astrophysical phenomena which can produce such black hole with 1 to solar mass. So if we someday find such an object, then we can say more about this dark matter interpretation of such black holes. And in this regard, there are lots of challenges regarding the distinction between such a black hole and a neutron star, because neutron star mass and this type of black hole mass are just in the same ballpark. So you can look at in new archive arrivals which discuss these things. One paper from Divya Singh and another paper from Shulagna Bhattacharya. So there's an interesting discussion about it. So thanks for listening.
Thank you for the nice talk. So you said you're forming this BEC out of these dark matter particles at the core of the neutron stars, but there is also interaction between dark matter particles and the baryons. That's always happening. Does that affect your BEC formation criterion?
So here I have considered the thermalization via dark matter neutron interaction itself. Then it's
Yes.
it's just a free gas approach in statistical mechanics what we do. So this TC only depends on the number density of dark matter. So first is thermalized with dark matter neutron interaction, and then it's just like a gas inside it, and
But it just continues to interact with baryons, right?
yes, but that interaction is not included here in the TC itself.
Okay. I'll talk to you later.
Okay.
Hi Deep, thanks for the nice talk. So I have a question which, when I also did this, I did not take into account. So there have been studies which talk about that in the capture rate, nuclear effects can drastically decrease the number of dark matter particles that you capture. And that depends on
Nuclear effects.
Nuclear effects, yes. And when you do it, do you take into account that?
No, I didn't take it. So what kind of nuclear effects you are saying?
So we can talk about it.
Okay,
There are things by Nicole Bell where she takes into account multi-nuclear or something. I mean, I don't understand it properly, and I have not taken that into
No,
account.
it is a
I was not done
simplistic
it.
kind of
Okay.
capture rate I have assumed, just to show the effect of neutron star temperature evolution, but I didn't take that.
Okay. Thank you very much. Thanks.
Achha, okay.
Any other questions?
Hello, thank you for the nice talk. So, from what I understood, the endoparasitic black hole requires this sufficient amount of dark matter captured by this old neutron star. But I might have missed it. But how much time does it take for this neutron star to capture the sufficient amount? For
So roughly 10 to the power 6, 7 years is enough. I have checked that. So, but depends on the thermal state of dark matter. But 10 to the power 6, 10 to the power 7 years is you can form this kind of black holes.
And one other follow-up. This is not only possible for neutron stars, white dwarfs.
Yes.
Yeah.
That can also happen for that. So, but for that, these constraints would change because the this baryon density is different in white dwarfs. So you can do that, right?
Maybe a quick question on in the reply you gave. The very fact that we have seen neutron stars of ages more than this number in our own galaxy, what constraints can you already put on this? Because if the neutron stars are eating up some dark matter to become a black hole in a time scale of a few tens of million years.
So from there, so I have taken this 10 to the power 10-year-old neutron star and I put this bound. So you just locate a isolated old neutron star, measure its age from its period and change in periods. From there, you can constrain these things.
So if this is already constrained that at high redshift, the chance of the neutron star to eat black holes will be not that efficient anymore, right?
So these constraints coming from in today's Polter, in today's universe, from z equal to 0, I guess.
Yeah, but we can talk about this later. Thanks.
Okay.
Let us thank Deep. The last speaker of this session is Ranjini Mondal, and she is going to talk about